All right, so we're going to tackle this. This French mathematician was able to take what was previously unknown about indeterminate forms. Okay, indeterminate forms had existed for centuries. Okay, way back. The Mayans knew about indeterminate forms. The Greeks and the Romans knew about indeterminate forms. But you would get to the end of an indeterminate form and then just sort of like quit because they couldn't do anymore. All right, once Leibniz and Newton developed the concept of a derivative, L'Hopital figured out that he could apply the concept of a derivative to the indeterminate forms that they'd gotten stuck on before, and then that allowed them to get over that hurdle, and now you can solve an indeterminate form. And it's something that I've said before, here's an indeterminate form and you can't do it yet, and you don't know about how to do it yet, but it's coming. And now that you know enough about derivatives, we can do it. So that's where we're at. All right, we have L'Hopital, which has a special rule. It's going to be applied to 0 over 0 and infinity over infinity. The BC group, they have saved infinity times 0 as another indeterminate form. You don't have to worry about that. You only have to worry about 0 over 0 and infinity over infinity. All right, that's what we're going to tackle today. All right, so just as a reminder about how math works in division, if you have 0 in the numerator, what will the result be? 0. Okay, 0 in the numerator means the result of that value is 0, no matter what the denominator is, as long as it's not also 0. If you have 0 in the denominator with something else in the numerator, that produces infinity. It could be plus or minus infinity, depending on what the numerator is. But then we got to, all right, we were introduced back in August to the first time you'd heard about, well, what about 0 divided by 0? And that was that indeterminate form. We did have some ways to handle that before. We were able to divide. We did GCF, we did factoring, we did foiling, and we did dividing through by the highest power. That's what we've been able to do with indeterminate forms so far, but now I'm going to teach you the next one. All right, so if you have infinity divided by anything, that still remains infinity. So infinity in the numerator, just like 0 in the numerator, that's the same thing. If you divide by infinity, you're dividing by this massively large number, and that's going to get you 0, but there's a plus or minus. So you're either going to be on the positive side of 0, or you'll be on the negative side of 0, one or the other. You'll be really close, approaching 0, but it'll be one or the other. And then finally, if you have infinity over infinity, that's indeterminate again. So we're going to focus on those two forms of indeterminate, and what do we do when we come across them. Here was a famous limit that we, again, previously learned in chapter 1. I proved it to you graphically. That was the only way that at the time we could prove what the answer was going to be. We looked at the graph of this, and the graph started out and then came up with a peak and then came down and then recompressed like that. All right, so what is the value of that limit? A. Okay, whatever A was. Okay, it doesn't ever get to A. There's an open hole at A, but we looked at the graph to assume that the left and the right-hand limits were A. Today, I can finally prove it to you. So again, here was the visual of the graph. We crunched or smushed the graph in between the hyperbola branches, and that hyperbola branches made this thing compress, and then we had that peak right there, that open circle. That was the only way we tackled it. All right, so for millennia, thousands of years, mathematicians had a hunch, a feeling, okay, a little spidey sense or whatever, like I'm pretty sure that, it's like this one, like it's got to be A. It can't be anything other than A. It looks like A, it should be A, but they could not prove 100% beyond a doubt that it was going to be A. Okay, we had the same thing with lots of other indeterminate forms. They just kind of had this feeling, but they couldn't prove it. Okay, so bring in our French mathematician. You don't really need to ever know think of spelling his first name right, but L'Hopital. All right, that's the guy. So from here on out, I told the BC students yesterday when I met with them during 5th period, I was like, hey, guess what tomorrow is? L'Hopital's rule. And they were like, yes, that's the best rule. So they're excited for you that you get to learn it. All right, here was L'Hopital's rule. L'Hopital figured out that if the limit of f of x and the limit of g of x are both 0, in other words, numerator and denominator both are 0. We call that an indeterminate form. He didn't have that word at the time, but he just said if the numerator and the denominator both turn out to be 0. And, of course, presuming that they are differentiable. Remember, if I tell you something's differentiable, what are you guaranteed to know that it also is? Continuous. So he's got both of those. It's got to be continuous. In other words, it's got to be continuous, and there can't be any corners or cusps or vertical tangents. Okay, so those are the caveats, because if you're using calculus, you can't have corners or cusps or vertical tangents. He was able to discover that the limit could be replaced with the derivatives. If the numerator and the denominator both turned out to have a limit value of 0, he discovered that you could replace the numerator and the denominator with the derivatives and end up with the correct value for the limit. This only works on quotients. It doesn't work on products. It doesn't work on subtraction or addition. It only works on a quotient that is in indeterminate form. He further was able to develop that if it's infinity over infinity, that you can replace the numerator and denominator with the derivatives and then proceed. Okay, so these are equal in value. We can use L'Hopital's rule to prove what we are very confident that the derivative of this is, sine of x over x. Okay, we are confident that that derivative is going to come out, or that limit value, is going to come out to be 1, because the a of the peak of the graph is going to be 1. But can you prove that it's going to turn out to be 1? If you do direct substitution, you get the sine of 0 over 0. Which is 0 over 0. You have to show me, you have to show me that the indeterminate form was part of your work. If you skip over the indeterminate form, then you haven't justified the use of L'Hopital's rule. So I need to see that you turned out to get an indeterminate. Yeah. Do you have to do that on the Yeah. Unless it's multiple choice. On the free response, yes. All right, so since it turned out to be indeterminate, we can replace the limit with the two derivatives. So what's the derivative of the top? Cosine x. What's the derivative of the bottom? 1. Now plug 0 into that instead. And I get cosine of 0, which has a value of 1, and I just proved that it turned out to be 1. So again, that spidey, tingly sense that you had that it was supposed to be 1, it had to be 1, the graph looks like it's going to be 1. Here's the algebraic proof that it turns out to be 1 using L'Hopital's rule for indeterminate forms. No, I'm not going to go through L'Hopital's huge proof. It's a whole book. All right, let's try again. Okay. How did he figure that out? It was his life's work. Okay, let's prove that L'Hopital's rule is available to us here. So we're going to drop in 0. So that'll give me 4 plus 0 minus 2. That'll give me 0 in the denominator. Sorry, not minus. Which is 2 minus 2, which is 0 over 0. So I have a legitimate case that L'Hopital's rule is, I can invoke that here. You'll probably want to pre-write on the square root. So you'll want to say, oh, that square root has a half around it instead so that you can do your derivative. then L'Hopital's rule says go ahead and use your derivative rules. So on the top, I'm going to have 1/2 times 4 plus x to the negative 1/2 times the chain rule of 1. So that's the numerator. And then the denominator is the derivative of 1. You never want to leave a negative denominator, so clean that up. The numerator is 1. The denominator has a 2. Yeah. It's from the derivative of 4 plus x. It's the chain rule. Okay, the inside, the derivative of 4 is 0. The derivative of x is 1. All right, so then my denominator would be 4 plus x to the positive half. And then I'm going to plug 0 into that. And I get 1 over 2 times 4 plus 0 to the half. That's 2 times the square root of 4. That's 1/4. So the limit value doesn't stay indeterminate anymore. The limit value is 1/4. Such a great and useful rule. Okay, we'll try it again. Furthermore, in subsequent chapters of his life's work, L'Hopital was able to figure out that if you do it once and you get the derivative, but you still are indeterminate, that you can do it again and do it with the second derivative. And if that's still indeterminate, you can do it with the third derivative. And you can keep applying derivatives as long as it's indeterminate, and you will eventually end up with the value of the limit. So you can repeat the process over and over as long as you keep getting an indeterminate form. So that's why the n is here, to represent an unlimited number of derivatives until you finally get away from an indeterminate form. But again, this only works on quotients. So if your problem's not a quotient and you can't make it a quotient by rewriting it, for example, is tangent a quotient? Not yet, but could you make it a quotient? Yes, you can make it sine over cosine. Okay, so if the thing is not yet a quotient, you can then not yet use L'Hopital's rule. So it has to be a quotient and it has to be indeterminate. So even though tangent does turn out to be a quotient, tangent is not indeterminate, and so I wouldn't use L'Hopital on it. So some people get really excited to use L'Hopital, and they use it when they're not supposed to, because they think, oh, I see a quotient. Great, I can use L'Hopital. You can only use it if it's a quotient and it's indeterminate. All right, so let's try this one. Always check to make sure it's indeterminate. So drop the 0 in. That's going to give me 0 times the sine of 0 over 0 cubed. That for sure is 0 over 0. So I am justified in using round 1 of L'Hopital's rule. Round 1 of L'Hopital's rule says 1 minus the cosine of x over 3x squared. That's round 1. That's the derivative of each of those terms. Then I'll drop 0 into that. So I'll get 1 minus the cosine of 0 over 3 times 0 squared. So I've substituted 0 in. The cosine of 0 is 1. So my numerator is 1 minus 1, and my denominator is 3 times 0. So I get 0 over 0 a second time. And so which means I'm justified in using L'Hopital for round 2. So I can do it again. And I try and see if that works. The derivative of 1 minus cosine x, that's going to take me to positive sine x. And the derivative of that is 6x. So that will give me the sine of 0 over 6 times 0, which once again is 0 over 0. Which means I'm ready for round 3. Will there eventually be an end? Okay, will there be an end to the numerator? What kind of function am I working with in the numerator? Is it a log? What is it? It's a trig. And what do trig functions always do in their derivatives? They cycle. Okay, cycles. So the top is just going to cycle back and forth. The bottom, what kind of function is that? What did it start out as? A cubic, which is a type of polynomial. Polynomials don't cycle. Polynomials descend. And eventually this polynomial would descend. And so I get cosine of x, which is a trig, but my denominator finally gets me to the number 6, which means when I substitute in 0, I get the fraction 1/6. So I could have graphed this function and had a pretty good feeling that the limit was going to be 1/6. I would have seen an open hole there, and I would have probably gone, yeah, God, it really looks like it's going to be 1/6. But if you don't have your graphing calculator, you wouldn't see that. And then this is the way to prove it without just looking at the graph. Okay, so what I'd like you to do in this question is to see if you can figure out where the mistake is. Okay, this student has repeatedly applied L'Hopital for multiple rounds over and over and over again. Can you figure out where they went wrong? Okay. So you can go ahead and write on your notes. Go ahead and try and figure out what they did wrong. I'll give you about a minute or so to try that. All right, let's see if we can figure out where the mistake was. Jonathan, did you raise your hand?
I found it, yeah.
You did find it? Where do you think it happened?
The second limit of x approaches 0, sine x over 1 plus 2x.
Mm-hmm. What's the problem?
The sine x on top becomes 0, but the 1 plus 2x on the bottom becomes 1.
Okay.
So you get 0 over 1, it isn't indeterminate.
Very good. This is no longer indeterminate. So this one turned out to be 0 over 0, which is indeterminate, so that's fine. But the second round does not turn out to be. You get 0 over 1, which is no longer indeterminate. And so the answer is not indeterminate. The answer is 0 over 1. What's the result of 0 over 1? 0, because 0 is in the numerator. And so that's no longer indeterminate. But you just see how it could be tempting to just keep staying in the rhythm of doing the derivatives over and over and over again until you get to the end. All right. Yes. Oh, sorry. I gave you another slide where you could do that. This one did turn out to be 0 over 0. This one turned out to be 0 over 1. So not indeterminate. All right, great. All right, last one. Okay, we're going to try plugging in pi for this one. So we're going to get the cosecant of pi plugged in and 1 plus the cotangent of pi. The cosecant of pi is coming up where there's an asymptote for cosecant. And so that would be a value of infinity because it's an asymptote. 1 plus the cotangent of pi is 1 plus another asymptote. So we have, and so when you add 1 to any infinity, you're going to have the indeterminate form infinity over infinity. So this is a different kind of indeterminate form, but one that still would result in us using L'Hopital. So we're back to the precision of our notation, right? We're using good equal signs. We're using limit anytime we are working with a variable. Once you move away from a variable and you change it to the value pi, you don't need limit anymore. But as long as you're back to working with a variable, then you're going to want to include your limit notation. So I need the derivative of cosecant, which is the negative cosecant x cotangent x. And then I need the derivative of 1 plus cotangent x, which is negative cosecant squared of x. At this point, you always want to look, is there anything I can do to simplify this And you notice that the numerator does have part of a cosecant expression, and the denominator does as well. So we can do some simplifying here. So I'm going to reduce a cosecant from the numerator. I'm going to reduce the squared from the denominator, and I'm going to clean up the negative signs. So that gives me cotangent x over positive cosecant x. If I plug in pi here, I get indeterminate again, which doesn't mean that I need to keep doing L'Hopital. I need some trig simplification, because cotangent over cosecant is, yes, it's a quotient form, but it's got lots of quotients in it, so we should simplify that. So we know that cotangent is cosine over sine. That's cotangent. And then we know that cosecant is 1 over sine. So this is not really a true quotient because it's got too many numerators and denominators. So rather than having that extra layer, we're going to multiply by the reciprocal, which is the sine of x, over 1. So that's what we want to do, is to simplify that so that we can get down to a true, something that can be evaluated. So that gives me the limit as x approaches pi, and the only thing that's left is the cosine of x, because I've reduced everything else away. So it's not a quotient anymore. Should be able to simply evaluate the cosine of pi, which is -1. So this limit value is -1. You can always check and verify on a graph, does that look like it makes sense if I'm graphing this equation, or look at a table and see if the table is approaching 3.14, -3.14159. But again, looking at a table or looking at a graph are never enough on its own. You've got to support it algebraically.